Hi, I'm Matteo Biagetti, currently based at the Institute for Fundamental Physics of the Universe in Trieste. Today, I would like to talk about work I've done with Alex Cole and Gary Shu about trying to bring topological data analysis into cosmological applications. Actually, these methods, and in particular persistent homology, which is the method we will use, has been already studied in the context of cosmology, looking at trying to understand the morphology of the cosmic web and large-scale structure. We tried a different approach and really tried to use this topological data analysis to provide cosmological constraints on cosmological parameters. So really from a data set, for instance, a galaxy survey, galaxy catalog, to constraining cosmological parameters with topological data analysis. A conventional way of extracting cosmology from bias tracers, so in general traces of the dark matter field. In this talk, I will have in mind galaxy catalogs in particular, is computing large-scale correlations, right? So we compute galaxy pairs, and also the three-point function in the last few years has been used in galaxy survey analysis. So we compute large-scale correlations to extract cosmological information, and we do this for a simple reason. We have predictions, okay? So we can solve perturbative equations that tell us what should be the two-point function that we observe of bias tracers, and we we can also compute theoretical errors that we are making. And not only that, but we can also complement the study and test the perturbative expansion, the perturbative modeling with n-body simulation. So the perturbative method can work only up to a certain range of large scales, up to mild nonlinear scales, and then n-body simulation can fill up information at nonlinear scales. It can only also test the predictivity of the perturbation theories. So these are the advantages, and the challenges are that are nonlinearity. So we cannot use all the modes that we have in galaxy surveys. Dark matter is nonlinear, meaning that because it has undergone gravitational instability, gravity coupled short with long modes, then its distribution is non-Gaussian, and perturbative theory cannot reach nonlinear regimes. And of course, we don't observe dark matter directly. We observe galaxies, for instance, and the relation between the two statistical distribution of the galaxy and dark matter are related, but are biased. And this bias is nonlinear on ranges of scales that matter in galaxy surveys. And then, of course, we observe galaxies in redshift space, and this also is a source of nonlinearity. Now, suppose that we kind of, for a moment, give up our predictivity and treat this galaxy catalog, like galaxy positions in the sky, as a discrete set of data points, or a point cloud, if you want, and still want to describe its properties. So in other fields of science, when having to deal with discrete set of points, one of the methods is to study their topology. So study topological features that that can be found in this discrete set of points. And in 3D, and this can be done in very general settings, even in field space. It can be done for different types of geometries, and it's a very well structured algorithm and mathematical. It's a set of mathematical theorems. But in our case, in which we are in 3D, a simple 3D setting, there are basically three possible features that can be found in this type of data. We can find connected components, which are made by connected galaxies at a certain distance. And these connected components can be long or short, depending on what distance I allow to connect two galaxies. We can close these snakes and make loops. And we also can, and then we can have voids. So these are three-dimensional surfaces made up by voids and are empty within. So they are voids. So differently than other cases, these three topological features are connected to something observable in a scale structure. So connected components can trace clusters. The loops can trace the filamentary structure of the cosmic web, where filaments intersect. Then we can close curves made with galaxies, and we know that many galaxies reside in filaments. And voids are voids. We are already using them in cosmological applications. And it's in this case, we are kind of tracing higher order correlations, right? Because of the non-trivial shape of these features. And but the challenge now is that we don't have clear theoretical prediction for what we should see. So for a certain catalog, so this example I'm showing here, by the way, is an n-body simulation that we will use for our analysis. These are dark matter particles. And the color coding is density. So we can find a set of halos in this case. So a discrete set of halos, and the amount of features that we find as a function of a distance with which we connect halos is very hard to predict. And therefore, we need to rely on n-body simulations or representation of or real data. And of course, in cosmology, it's a huge problem, right? Because well, if we could simulate the whole universe at arbitrary precision, we wouldn't be talking about this. But we can't. So so it's important that our method doesn't require at least higher computational cost than it's usually done. So I will try to convince you that I think we have kind of a way of making the computational cost as heavy as it already is. So imagine for a galaxy survey, we run a set of mock catalogs that are supposed to reproduce the geometry of the survey and also the number density and all the properties, and we study them to predict what we will see in the survey, and then also we compare the survey to these. So these, with the methods that we find, these might be enough. All right, so let's see how this works. So as I said, topological data analysis is about computing the shape of discrete data via its multiscale topology. So multiscale here means that what I said, I can dial the distance between halos with the successive coarse grainings, right? So, and when I do this, features will be created and destroyed. So for example, this loop, if I say that the distance with which it connects two galaxies or halos is greater than this shortest semi-x, for instance, this will be just destroyed, no? I will show you an example in a second. And so, well, so this type of analysis it has successful applications in other fields of science. So in physics, it's kind of coming a bit later because we had predictions, right? So but nevertheless, I think it's interesting to explore these methods, and especially because, as I said, they kind of trace high order correlation functions. So we hope that we provide complementary information to studying low order correlation function. All right. So because I don't have time to talk about the topic in detail, I will just use examples to explain what this method is about. You can refer to the paper or to me if you want to have more details. So let's consider a set of points. Point cloud, a simple one is this one. If I ask a computer what this is, it will tell me it will tell me the coordinates, for instance. But as a human, without needing to write any code, of course, we see that this is a circle, right? It's a noisy circle, but still a circle. So now, persistent homology is basically supposed to see this circle. And let's see how. So let's define a filtration parameter, nu, which in this case is represented by the radius of this ball around each point. So we draw a ball around each point, and then we say that if two balls touch or superimpose, we can connect two points or vertices in so-called vertices into edges. So we can connect them. And then we start forming these connected components that I was showing before, and another structure. So in 3D, these structures are called simplices. In 3D, I can form, in 2D, as in this case, I can form three simplices: the vertex, the edges, and the triangles. So it's like field objects. And so this here provides a simplicial representation of your data with filtration parameter nu equal 1. And now in this simplicial representation, we find homology classes of topological features. So as I said, we find connected components. At this level, there are no loops, and voids do not exist in 2D. If I then increase the radius of these balls, I start forming more structure, and I start seeing the first loops. So here there are the two loops. So as you can see now, we start seeing that very soon all the balls will connect, and we will see this central circle, which we do at a certain value of this filtration parameter. So now the clear feature is this one in the middle, and the particularity of it is that so here also there were features, but because they were noise, they died very quickly, right? So if we go now this loop that was there is not there anymore. While this central feature here is supposed to live longer. Live means that it survives more and more coarse graining transformations. And at a certain value of nu, this will disappear and just become a full chunk of data. So, okay, so now how do you make this a bit more quantitative? So as I said, persistent homology is about finding this simplicial representation, associate each step with a filtration parameter so that they are ordered, so that the low order parameter filtration representation is included in the higher one. And classify and classify topological features by their birth scale, meaning at which nu they are born, and their death scale, so when they die, or more specifically the persistence. So it's the death minus the birth. So here we have. So let's see this in an example. So another example can be like two noisy circles like this that are intersecting. So these are just coordinates. And this is the diagram of births and persistence. So I track where where each topological feature is born and how long it persists. So here green circles are loops, and blue are connected components. And in this diagram, it's clear that what clearly stands out are these 3 points here that are very high persistence and they're born very early. And these are these three dots, these three loops here. The rest is clearly noise, right? So here the intuition works well, and this is how we represent basically our topological features with the persistence diagram. So now we want to apply this to cosmology. So I talked about galaxies. That would be the case of applying this to real data directly. But we decided to first start from a simplified scenario where we have an embodied simulation in a cubic box, and we have a halo catalog. So no, we don't paint halos with galaxies. The reason for this simplified setting is that we can have everything under control to develop a pipeline. And we do this trying to constrain a single cosmological parameter, which will be primordial non-Gaussianity. And of course, this is a simplified scenario. The real case scenario is where you have a galaxy catalog in a light cone. You don't know the cosmology, and so on. But we first developed this method in this setting, and then plan to generalize to a more complicated setting. Although the basics that we found are applicable to a real case scenario. Of course, so we just constrain a cosmological parameter, a single one, but we do also a preliminary study of multiple cosmological parameters and degeneracies, and try to study the physics of topological signatures. I said we cannot predict them, but we can study them a posteriori. And actually, we use this as a guideline for how we look for the cosmological parameter. In the interest of time, I will actually only talk about the first point. And again, you can refer to the paper and ask me in the discussion session if needed. Okay, so yeah, I guess so the cosmological parameter we want to constrain is primordial non-Gaussianity. Why? Well, the one line answer is that we had simulations for it, but it has interest in its own right. The only thing I want to point out is that our pipeline doesn't care about that it is primordial non-Gaussianity or not. It's applicable to any cosmological parameter. Then primordial non-Gaussianity. Okay, so if you have seen Horkan-Oreño's talk, that's a very nice overview of why primordial non-Gaussianity is interesting. So I suggest you look at that. Here I'm just providing a one-slide summary. And so, yeah, so primordial non-Gaussianity refers to the statistical distribution of primordial perturbation being non-Gaussian, meaning that the 3-point function or 4-point function, the n-point function with a higher than 2 of the primordial perturbation is non-zero. And it's interesting because this is related to interactions happening among fields during inflation. So interactions source these non-Gaussianities. And right now we have constraint on the power spectrum of inflation. We have observed a spectral tilt, which is not exactly 1, and this is a prediction of inflation. So this is kind of a probe in the free theory, but we haven't detected any primordial non-Gaussianity yet. And this would help us understanding a mechanism of production of primordial perturbations, and also know about the particle content during inflation. So it's not only about a question of the history of the universe and the initial conditions of our universe, so a cosmological question, but it's also a high energy physics question that it's interesting to ask because of the high energy involved during inflation. The type of non-Gaussianity that we input in the simulations is a local type, which is, so if you take the primordial perturbation field, we expand around the Gaussian. So there's a Gaussian, and then we have a term going like zeta squared with some parameter. And if you compute the 3-point function normalized by the power spectrum squared, it's proportional to this parameter. And this type of non-Gaussianity peaks in the squeeze configuration. So when the triangle of momenta is squeezed on one side. It has to be a triangle because of momentum conservation. Why is this type of non-Gaussianity interesting and famous? So there are consistency relations in inflation that are give a kind of a strong results on this local type non-Gaussianity. They say basically that if primordial perturbation are produced by a single field, then this non-Gaussianity of this type has to be very, very small. So there is a minimum amount called gravitational floor, which is although very small, is proportional to slow roll parameters and the ratio between the long and short side of this triangle. So any detection right now would be a signal of multi-field inflation. This is kind of a nice statement, that a nice knowing that there are more than one particle during inflation. And the current constraints are at 1 sigma around 5, the best constraints from the CMB. Okay. Yes, one more thing. In local primordial non-Gaussianity, unbiased tracers have a kind of a famous effect, a strong scale dependence at large scales when you compute the power spectrum. So the halo power spectrum in this case, because I'm showing measurements from the simulation that we'll use, but the galaxy power spectrum is expected to show like 1 over k squared feature at large scales in the presence of non-Gaussianity. This is for FNL 250, so it's excluded, but just to show the effect. And here is FNL 10, which is the one that we will try to detect with respect to the orange, which is without non-Gaussianity. So I just want to point out with this that the signal when using low order correlation function is clearly at large scales. All right, so the data set that we use is embodied simulations. I'm not gonna give a lot of details, but just to fix a few points. So we have a set of simulation with lambda CDM, no non-Gaussianity, and a set with the same cosmology as the, let's say, call it the fiducial one, but for FNL equal 10. And we use these two, we compare these two to give constraints. We have then simulations with stronger non-Gaussianity to get physical intuition on the topological signature of non-Gaussianity. And then we have a small box, small simulation with strong non-Gaussianity, which we use for templates. This is important because it's kind of addressing the computational expense problem I was mentioning before. So we basically develop templates of non-Gaussianity that can be used to put constraints on non-Gaussianity. So we develop a template for the strong signal with the small volume, and we are able to use it for FNL10. This is important because it means that for any cosmological, for this particular cosmological parameter, and hopefully for all of them, you don't need to run giant simulations with this parameter varying. You just need to run small boxes and produce your template and then use it in real data. Okay, so this is the cosmology we have, and just to give the idea, we have a catalog of 10 million halos, more or less, at each redshift, and we will I will only show result about redshift 1. Okay, so now we are ready to draw our persistent diagrams. So this is the same diagram as before when I had this 8-shaped example, but for a halo catalog. So each dot is a topological feature. And this is for the fiducial cosmology, lambda CDM cosmology simulation. And each dot is a topological feature. And as you can see, it's not as evident as before that the very persistent features are up high in the diagram, and then the rest is junk. This is kind of a continuous diagram. So we need to understand how to extract information from these diagrams. This is what I will explain now. One point I want to make is that in order to be sure that we don't trace systematics in the n-body, we kind of cut these diagrams at 5 megaparsec over h. So we don't consider features at smaller scale than that. All right, so one way we can kind of get intuition is by taking diagram of this for Gaussian and non-Gaussian and kind of subtract them, right? So this is, you can build persistent images that are kind of density plots of these persistent diagrams and plot the difference between the two, which is what we are doing here for the strong non-Gaussianity case, so that we see very clearly. So in the strong non-Gaussianity case, this is the non-Gaussian minus Gaussian. This is what we find for loops and voids. So blue means that there are less features in this region in the non-Gaussian simulation than in the Gaussian one, and more in the red. So these images just clearly tell us two things. First, that birds are important here, right? So we should expect that constraints should come, strong constraints should come from bird in the persistent diagrams. And also probably death, which is on this line here. And that these features are at kind of a smaller scale than what we were showing the power spectrum before. So kind of 10 to 20 megaparsec, 30. But in the case of the power spectrum, we are looking for the scale dependent bias is at 100, order 100, right? So we are hoping that we are kind of tracing complementary scales as in the conventional, with respect to the conventional methods. So these persistent images tell us that it might be promising to slice the persistent diagrams in some way. So the way in which we get data from persistent diagrams is the following. Let's focus on the green curve, which is bird, which we said should be interesting. And let's do this. So we start from this curve being 0, and we count all the topological features on the right of it. And then we start, we divide this into bins, and we move this curve to this curve to the right. So we count less and less objects until we count none. So then this will give us this actually, if we normalize by the total number of features, this gives us an empirical distribution function, like this one that we are showing, this B1 and B2, and similar for the other curves. And this is for the Gaussian case, and then we can compare how this empirical distribution behaves with and without non-Gaussianity. This on the left is Betti curves. I don't have time to explain, but you can ask me in the discussion session if you are interested. All right. So now, how do we treat this bin, this vector of values? Like, right? I mean, we have bins, and we have a value for each bin to constrain non-Gaussianity. So the first test we do is a kind of an anomaly detection. This is a kind of a chi-squared. So we first determine a null hypothesis distribution. So suppose that, so what we do is to divide our simulation into a survey box and fiducial box. So the first test we do is to compare the case in which both the survey box and the fiducial box have the lambda CDM cosmology, so no non-Gaussianity. So basically, they have the same cosmology. Now, there are still differences because of cosmic variance. We are careful not to couple the same initial condition in the simulation, so they are different realizations. So this gives us kind of a baseline for detection, which is this gray histogram here. So any parameter we want to constrain has to be more significant than this histogram here. And then we repeat the same exercise when we put in the survey boxes the primordial non-Gaussianity. And this is the orange curve. So now, if these were Gaussians, we could just say what is the 2 sigma or 3 sigma significance, but in principle, they are not. So what we do is that we count how many points in the histogram, orange histogram, are in the 95th percentile of the gray one, which is kind of a, and we find around 60% significance of finding FNL equal 10. And these are the best statistics. We try many of them, and the birds And the DES, as I was saying, give the best constraints as expected. The other thing I wanted to point out is that the features are at around 10 megaparsec, as we saw before. So we're kind of still seeing FNL10 in these complementary scales. So I will conclude now with the template idea. So now we were just fishing for a parameter. In this case, we knew which parameter, but in the real case scenario, you don't. So one degree of complication we can add is actually targeting a parameter, which we do by building templates, as I was saying before. We take strong non-Gaussianity, we subtract these topological curves, the non-Gaussian minus the Gaussian one, and then we dot this template vector with the survey one. So if they are parallel, we expect that that parameter is in the survey. If we are orthogonal, then we expect not it to be there. And we repeat the exercise as before. So we have like distribution for null detection. So just cosmic variance, where we put the same cosmology both in the survey boxes and the fiduciary boxes. And then we do the non-Gaussian one. And as you can see here, we can detect a non-Gaussianity with higher significance. And this is because we are not just looking anywhere in the vector space of the data, but just in a specific direction. So main results are that, well, we do see FNL10 with a degree of significance. And in principle, these are complementary scales with respect to the conventional method of looking at the power spectrum. This just means that if in the future this method is established, it's a long way to go, but imagine that, then we would need we still need large volumes, but we don't need large scales. So even a deep survey, but that samples a lot of galaxies, might be good for non-Gaussianity, which is kind of a new thing. And then the pipeline can be applied to any cosmological parameters. So of course, we worked in a simplified setting. We only had one varying parameter. Actually, we worked on degeneracies a bit. We tested this template method when we put a wrong template on the survey data, and we find that it works, but it was a simplified setting. So we want to go to constrain multiple cosmological parameters and eventually to real data. Also, it's interesting to look at other types of primordial non-Gaussianity. This persistent homology is particularly good in principle with oscillating features. So those type of non-Gaussianities can be promising. And that's it. Yeah. So thank you again for the organizers to give me the opportunity to give this talk, and see you at the discussion session.